No, that's okay. No. Please try to answer this question while I'm logging on.
I made a quick estimate how many people we have here. I guess it's about 200, plus minus 1. So answer, what is the correct answer? So what we are saying here is that you have 5 systems, and 4 of them are identical, and 1 is different. Which one is different? Of course, you will have to apply one of the rules for block diagram simplifications. And I think at least in the lecture notes, that would be rule 3. Those rules, they don't have particular numbers assigned to them depending on how you list them. But this would be a rule for a feedback loop. So if you remember those rules, or if you don't, you can have a look and decide which of the 5 would be different from the other 4. And I'll give you 1 more minute, and then you tell me. Okay, your minute is up. So which one do you think, if you have one single opinion, of course, 200 people, so which one is the right, which one is different from the others? A, B, C, D, or E? D. Do we all agree with D? C. Other opinions? So C or D seem to be the favorites. Does anyone think it's A? How many of you think it's A? Quick show of hands. No one. How many of you think it's B? 1. How many of you think it's C? Oh, that's a lot. Yeah. More than 1/3 of 200, which is, say, 80. How many of you think it's D? Okay, that's a reasonable number. My estimate is 50. So how many of you think it's E? 1, 2, 3, 4, 5, well, say 8. Okay. Good. So the numbers don't add up, as usual. So what do we do about the rest of you guys? How many of you don't know? Okay, that's very honest. Thank you. It's about 6. Thank you. How many of you don't care? Or couldn't care less, should I say. CCL. Okay. No one? Okay, that's good. So what is, we still need numbers. H. How many of you do not want to communicate with the lecturer? Okay. Well, those who don't want to communicate, they won't show their hands because that will be communication, so I'm not surprised. Okay. So some of you have their own reasons why they're not telling us their opinion. Okay, don't worry. This is not... Obviously, we are trying to put a democratic process in place, so if you express your opinion, you shouldn't be penalized, in theory. Okay? But this is a classroom, not a parliament, so yeah, maybe you're right. Be careful what you say. It can be always held against you. So let's see, 80 seems to be the favorite, followed closely by 50. We have some people opting for E. So let's quickly derive the transfer functions of each individual system. So this is a negative feedback loop. That means that the transfer function is going to be GO over 1 plus this transfer function times this transfer function. Now, what is the transfer function here in the feedback loop? 1, okay? So it's 1. So it is GO times 1. So the transfer function here is GO over 1 plus GO. Let's see over here. Case B, we still have GO in the main loop, but this is a positive feedback loop. So it is 1 minus, and now the product of these two, which is GO times minus 1, which will become GO over 1 plus GO, which is the same. Okay. Now C, let's see. First, we have a negative feedback loop. So G equals to minus GO over 1. It's a negative feedback loop, so it's 1 plus minus GO times 1, so it is minus GO. And then times minus 1 over here. And that will give us GO over 1 minus GO. So it seems to me that the majority is right. So at least in this case, the majority is right. So if you guys vote for the Prime Minister, we'll get the best possible Prime Minister. Okay, now let's see the other two, because there is something interesting here as well. So G equals to minus 1, obviously, times minus GO over a positive feedback loop, so it's 1 minus GO. These two minuses will give us plus GO over 1 plus GO, which is the same as A and B. So a significant number of you got deceived by these two minuses or whatever else deceived you. Let's see E. Transfer function equals, so it is a negative feedback loop. Up here is minus GO. Down here is 1 plus. Now minus 1 minus GO, which is minus GO over 1 plus GO. Now this one looks exactly the same as A, B, and D if it wasn't for this minus. Now this minus, as strange as it may sound, doesn't make the system different. It is the same system. What this minus indicates is that it may be only a matter of sign convention. So what we adopted early on as a positive direction, it is still the same system. It is just the orientation of the axis that we introduced. Nothing more than that. For example, if this was not clear, our well-known system. So you have force acting downwards, and you have displacement x. If you decide that x is positive also downwards, then you have transfer function x of s over f of s, fi of s, will be some transfer function g of s. Okay, and we know what that transfer function is. But if you decide, for whatever reasons, that this is the positive direction of x, then your transfer function x of s over fi of s will be equal to minus g of s. Did we change the system? No, it is the same system with the mass and the spring. Exactly the same spring, exactly the same mass. The only thing we changed is the orientation of this axis. So you decide to call this positive. Maybe we have a reason for that. Maybe we are just not thinking very clearly. But we didn't change the system. Okay. So this minus back here, this minus doesn't make the system different. It is just the sign convention that is different, nothing else. Okay. Which means, if that is to be translated into response of the system, so in one case, if this is how the system responds, in the other case, it would be this. So same exponential approaching the same value, just this one would be minus a, this one would be plus a. Same system. Right. If there are no questions on this, let's move to our lecture on block diagrams, because if you remember, we covered only one problem. So what we did last time is we took a spring mass damper, so just slightly more complex system than the one we saw. Spring mass damper system, and instead of deriving the differential equation that describes this system, we decided to build a block diagram describing this system. And the next thing we did, we applied those 5 rules to obtain the transfer function using the block diagrams. Okay, so we are not repeating that. This is the block diagram, and then applying those 5 rules, or those that are applicable in this particular case, we simplified the block diagram until we obtained a single block containing the transfer function of the system. Now we are going to move to some other types of systems. So in this case, we have a water tank system. So 2 tanks. The one on the right is the one where we have flow in. And that's also where we have the flow out. There is another tank, and they are connected to this valve R1. The flow out goes through this valve R2. So now we have an option of writing differential equations describing all 4 components, 2 tanks, 2 valves. Or what we are going to do here, we are going to build a block diagram of this system. And we are going to do that by describing again each component by a differential equation. But we are not going to combine the equations to eliminate the variables we don't want. We want to build a block diagram. So the first tank here, the one on the right, we know the basic rule for a water tank, that the net flow into the tank equals to rate of change of volume in the tank. Net flow means all flows in, which is Qi, minus all flows out, which is QO2 and QO1, will be equal to the rate of change of volume, which is AHO dot. And that would be this equation here. This equation will be converted into a block diagram, or at least part of the block diagram. So Qi minus QO1 minus QO2 equals to AHO dot. So let's leave this part as it is until we finish all other components. The tank on the left, we apply the same logic, apart from there is only one flow in, which is QO1. There is no flow out. So the flow in, QO1, will result in rate of change of volume inside the tank, which is AH1. So we are not even writing this equation. We are simply saying that HO1 plus 0, minus 0, okay, there is nothing else, equals to AH1 dot. So this summation is effectively redundant, unnecessary, completely. Okay. Now let's define now the flow through this valve, QO1. What is QO1 equal to? First of all, it is proportional to the height difference between the 2 tanks. So it's the height difference that drives the flow through the valve. So it is HO minus H1. And it is inversely proportional to the resistance of the wall, which is R1 rather, sorry. So HO over R1 minus H1 over R1, or we can say HO minus H1, and then that difference divided by R1, which is what we are having here. So HO minus H1 times 1 over R1 will be equal to QO1. Okay, so QO1 is this. QO2, if you look here, QO2 depends only on height HO, because outside we have the atmosphere, so it is flowing into no other tank in particular. So it is HO over R2. So QO2 is HO over R2. So, or in other words, if you want to draw the block diagram showing this, HO divided by R2 equals QO2. So now all we need to do is combine these four like a puzzle and put them together to form a nice, beautiful block diagram, which is this thing here. Now, can you see how it is done? I bet 90% of you don't see that. That's why I'm going to switch the camera again. Okay, so back to individual components. Or actually, I'm going to suggest a particular way of building this block diagram, which doesn't mean that this is the only way. It is on. It was when I came here. I'll try once again, room control. Room control. It says running for another hour and 29 minutes. So it's not running very well. I noticed that throughout this building, maybe other buildings as well. I don't know. It's probably hot and humid and the air conditioning is struggling. So sorry, there's nothing I can do. I hope that's not why he's leaving. But. Okay, so what I suggest is, again, check the system carefully. What is the input? What is the output? And I would start like this. The input is QI. The output is HO. And everything else needs to be packed in between. Okay. I mean, it's up to you. If you want to copy what I'm doing, you will end up with exactly the same diagram as what you have in lecture notes. Maybe it's better just to watch what I'm doing step by step. But it's up to you. Okay, so let's start with the first. Okay, so if you remember, the first tank had this, QI minus QO1 minus QO2 equals to AHO dot. And I'm simply going to copy this over here into my big block diagram. So summation minus, and over here I have AHO dot. QO1, QO2, so I don't forget what these two arrows are. Okay, so I can already notice that I have AHO dot here and I need HO over here. So I need to do something with this signal to obtain this. Okay. Sorry. Okay. So copying this over here. So my next thought is how to use this to obtain this. Well, first of all, I'm going to divide by A. So now I have HO dot here. And then I'm going to integrate HO dot, which is 1 over S, So I have HO. Okay, so that main branch, if you want to call it, is pretty much completed. But I need to somehow create these two signals from the information available. So I also said earlier that HO, when divided by R2, was equal to QO2. We had that, I think. Yes, that was the very last one in your lecture notes. Oops, where is, oh, this side. Okay. So this part will help me create QO2. Okay, because that's what I need here. So if I take HO, multiply by 1 over R2, on this side, I have exactly what I need here. Okay. So this completes the bottom feedback loop, if you want to call it that way. So the last thing to find is QO1. Now, QO1, for that, I can use a couple of things. So, for example, I have HO earlier from the lecture notes, HO minus H1, and then divided by R1 will give me QO1. So that means I will take HO and I will have to subtract H1. So if I take HO and I subtract H1, I will see later where I am going to find H1. The result of this is going to be QO1, sorry, and that needs to be multiplied by 1 over R1. This is QO1, which is what I need here. So I solved this problem here, but I have created a new one over here. So now I need H1. So fortunately, I have another piece of puzzle I haven't used, which is QO1. Put it 1 or whatever you want. We had a summation with nothing else to add to it. And we have A H1 dot. Now, QO1, this signal is also equal to A H1 dot. So I'm going to take it back this way. So QO1 effectively the same as A H1 dot. And from A H1 dot, I'm going to create H1, the same way I did it here to create HO. So first, I'm dividing by A. So this is H1 dot here. And then I'm integrating. So I'm getting H1. Now, this is the block diagram of our two-tank system. If you compare with what's in the lecture notes, It is effectively the same, apart from in the lecture notes, these two are already combined into 1 over AS, and these two blocks are also combined into 1 over AS. So they have already done the first step in the lecture notes. The two blocks that are in series, we just multiply the transfer functions. Two blocks in series multiply the transfer functions. Okay, so maybe I'll stay with the camera because again the lecture notes don't give you exactly how this is done step by step. So let's do it again. Qi 1 over AS okay. HO, then I'll take it back here. I have another summation, minus sign. I have 1 over R1, negative sign here. Then I have 1 over AS, okay, and I also have 1 over R2. And I have another negative feedback loop here. So effectively, this is what you have in your notes. Okay, so if you are catching up, right? Oh, sorry, yeah? R1, R2, back in the system. It is the resistance of the valve. So R1 resistance of valve 1, R2 resistance of valve 2. Okay, so now we need to think what the next step could be, which of the known rules we can apply to further simplify this block diagram. Now this looks like a feedback loop, apart from we need to split this summation into two. But our bigger problem is what is happening up here. Okay, so what is this? Can anyone recognize what kind of configuration, what kind of loop we have here? I think I heard the right. It's a feedback loop. It may not look like one, but it is a feedback loop. Okay, so for this feedback loop, this is the input, this is the output, and this is the feedback branch. And this feedback signal is subtracted from the input signal. So it is a negative feedback loop, where G1 is this, G2 is this thing here. If you don't see it, I will just rewrite it. Or redraw it, rather. So this is equivalent to, now HO being the input, minus sign, 1 over R1. Output is Q1. Feedback loop, 1 over AS. We are more familiar with this form, when the input comes from your left and the output goes to the right. But in a real situation, you may have all sorts of combinations. So in this case, the input is coming from bottom right, and the input is leaving at the bottom left of our feedback loop. So it's not really, what is left, what is right, what is up, what is down, but really how the signal flows, or how signals flow. In this case, this will be the input into this block, this will be the output. Output taken back and subtracted from the input. That is the definition of a negative feedback loop. So this one only, let's stay with this since we are doing it. This one will give us a new transfer function, HO, 1 over R1 over 1 plus 1 over A R1S. I hope you can read this. Q1. Now back to our main block diagram. Qi. I'm going to separate it, just making sure I'm following what you have in the lecture notes. So I'm going to separate now this summation into two, as we did on Friday. Okay. So now, this part here, this summation, is the same as this one here. One over AS HO, down here it's 1 over R2, okay? But up here, I'm going to put this in place. Okay, so that will give me what? AS over 1 plus, oh sorry, yeah, 1 plus A R1S. Okay. So you agree that this new one is equivalent to the previous one? Okay. So if you agree with that, then the next two steps, I think, are rather obvious. Here you have a negative feedback loop, so we replace it with one block, and then we have another negative feedback loop. And that will give us our final transfer function. So now let's solve this one first. Okay, main branch, feedback branch. Next page. So G1 is A over S, 1 plus, because it's a negative feedback loop, 1 over A S R2. HO, no, I don't have enough room, so I'll go underneath. That's the same thing. AS over 1 plus A R1S. So this is QO2. This, just to simplify this is equal to R2 over A R2S plus 1. Okay. Does this look right? I think it does. So what is left now is the final feedback loop to be resolved. And that will give us Qi HO. Let's see what is in here. G1, which is R2 over A R2S plus 1 over 1 plus a product of the two. Okay, so it's A R2S over 1 plus A R1S 1 plus A R2S. Okay. Or Qi HO, and you have R2, if everything was done right, brackets, R1AS plus 1. Down here it's R2AS plus 1, brackets, open brackets, R1 AS plus 1, and now plus R2 AS. And this looks right. Okay. So this was another example, how you build a block diagram out of individual components, and then how you reduce that block diagram to get the transfer function. Single block containing the transfer function of the whole system. Any questions on this particular example? Okay, then back to lecture notes. Right, so this is, a few steps are missing here, but once again, this part we converted, we decided it was another feedback loop, we resolved that feedback loop, and now we have two feedback loops that look normal, just normal feedback loops, exactly as we did it here. Okay, this one we won't finish before the break, but let's try first. Well, let's begin. So we have an electrical circuit here, two resistors R1 and R2, and two capacitors C1 and C2. Input voltage EI, output voltage EO. Okay, we are going to introduce this E2, intermediate voltage here, so we can easier write the equations before we build the block diagram. So let's now write the equation describing this loop here. Here it is. EI will be equal to I1 R1 plus E2, where E2 is the voltage across these 2 points. Next equation describing this second loop here. So E2 equals to I2 R2 plus EO. I2 R2 plus EO. What I forgot to say is that if current here is I1, at this point it will break into two currents, I2 and I3. Okay, so that was the second loop. Now, voltage across these 2 points, EO, equals to, because this is a capacitor, it is equal to 1 over C1 I2, integral I2 dt. Voltage across these 2 points is actually voltage across the capacitor again. So E2 will be equal to 1 over C1 integral of I3 dt. So these are the 4 equations. Plus, fifth equation is the equation describing the relationship between three currents. So I1 equals to I2 plus I3. These two equations here are just the last two rewritten. Okay, so if you have an integral here, then I2 will be equal to C2 EO dot. And I3 from here will be equal to C1 E2 dot. So these 5 equations, it is not shown here, but you can do what we did earlier. Write little pieces of puzzle, 5 pieces of puzzle, that we will need to connect together to create a block diagram that looks like this. So what I suggest, I will disappear for 10 minutes, enjoy my break, and you will be building this block diagram. Okay, any questions? We can have the break. I know it's a bit earlier, but I think this is the right moment to make a break. And then after break, I'll do it, don't worry. Any questions? Yeah, okay, so let's have a break.
Because like you have Echo, and from what they know, Echo works on Microsoft.
Yeah. Because like when I use it, it like always bugs out. Sometimes like it'll just like skip back to the start, and then like your sync is out with the video and stuff. Like if you try and watch it, so it like always stuffs up. So I'm just like,
Even on Explorer.
yeah.
Okay, well, you are the only one. I mean, can you try different machines or instead of mobile?
But I can just work through it. But like, are you not gonna get the other system up?
Okay. I mean, I gave up after 2 weeks of trying the other method, so I'll try again. I mean,
I just wanted, like, I just
assumed no one was complaining. I assumed the problem was solved. So obviously it's not.
Yeah, that's right.
And well, since these guys are doing their job, I should probably try. Yeah, that's right. But the problem, I mean, if I say I'm too busy, well, everyone will say that, even though I'm not busy.
Yeah, no.
But you know, I do have too much support this semester, and I really, you know, if it was something simple, if I knew what I was doing, I would do it. Yeah. If it takes time, but you know, I keep doing things that it's like over. You know, it's well,
that's not like I don't know how it works.
I know. It's not you. I mean, you know, it's me. But since I don't know how to do it, these guys are doing it. Yeah. So I'll try once again and see where I got stuck last time. Yeah. Because obviously you guys need the Echo is not perfect.
Or just like it'll be okay, but like if you ever skip forward or if like sometimes it'll just be playing and it'll just like skip like back a bit. As soon as you skip anywhere, it just like the sync and the video go out.
Sound
so
and
like
video.
you're explaining it and you're like, oh, if you look here at the equation x blah 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 blah, and it's just like showing like a block diagram. It's like, oh, the equation x blah blah, and it's like they're not the same, so you can't do it. But like,
thanks for that. So you're obviously not supposed to.
No, yeah, like I've been making ones that I can make, like I can't find the Friday ones, and then I have.
I'm obviously trying to get back to that.
Yeah.
I mean, that's I'll see what.
All right, I think we can move on. All right, I'm confident you've done the block diagram. So since you've done it, now you can check whether I'm right with what I'm doing here. So once again, here are the 5 equations that describe our system. And we are going to use these equations to construct the block diagram. And again, as recommended earlier, I will start with the input and the output. And now we are going to see how we insert everything else. So all these 5 pieces of information in between in order to get the block diagram. So the only equation here that contains EI is the first one here. So I'm going to use that equation. So here it is I1R1 to obtain E2. So E2 equals EI minus I1R1. EI minus I1R1. Okay, moving on. E2 minus I2R2 will give us EO, which is what we need over here. So this part was not very difficult. Okay. So we have the input, we have the output, but now we need to see where we can get these 2 signals from, I1R1 and I2R2. So what I suggest here, you go upstream in this case. So if you have I2R2, you ask yourself, how did I get this signal? And the answer would be, I multiplied I2 by R2. Okay. How did I get I2? Well, possibly using this equation here. So using EO, differentiating EO and multiplying by C2. So if I take EO like this, multiply by C2 and differentiate, I get I2. Okay, so this problem here is solved. Now we have this one, I1, R1. So let's apply the same logic first. So if I put R1 here, over here I have I1. Okay. Now, where does, yeah, I see some are still drawing. Okay, I'll slow down. Where does this current come from? I1. Well, I can use the last equation here. I1 is the sum of 2 other currents, I2 and I3. I2 is here. So take I2. And add I3. So here I have plus and plus signs. And finally, the last question we're asking ourselves, how did we get I3? And this is the last equation we haven't used. I3 equals to C1 E2 dot. So if you take E2, as we did over here, multiply by C1 and differentiate, we'll get I3. So C1S for differentiation completes our block diagram. Okay. Now, your block diagram does not have to look like this to be correct. Depends in which order you use different equations and how you connect different blocks. So this is just one possible correct solution, correct block diagram. Okay. But somehow this looks the easiest to solve, as strange as this may sound. So if you make it in a different way, that could be correct, but then solving, reducing the block diagram, applying those rules sometimes becomes extremely difficult. So let's see, this is not really easy. This is difficult, but it is not extremely difficult. So let's go step by step. Let's see what we can do here with this block diagram. It's hard to see really where we start. This part here looks like a feedback loop, but we can't really multiply these two because we still need this signal to go into this summation. So if we replace this with a feedback loop with one block, we lose I2, but we need to keep I2. Over here, well, again, this summation, it's not really a parallel connection because you have between this point and this point here, you have so many other things. So the only thing that kind of makes sense is to move this junction back over here. So that will be rule 4 or 5. I don't remember the number. But if I move this point over here, then I will have to multiply by whatever I have in here, if you agree with that. So that's what I'm doing. So the first part, the left-hand half will be the same. EI summation, another summation, EO. Now I will take two. One is, okay, C2S. I didn't leave enough room. Then R2. Then here we have a negative. And the other one, that's the one we moved. So just to indicate that, that's this one. We'll have to have C2S. Why? Because on this side, we want to keep I2. Sorry, I want to move to black. I want to keep I2. Why do I want to keep I2? Because I still need this summation here. C1S. I want to keep this summation in place because I need I1 here. R1. Maybe I made it too small. Yeah. Okay. So once again, by moving this junction over here, we still need to multiply this new line by, if this was G1, that's what we multiply with. So we keep G1 over here, which is C2S. Yeah. you multiply by whatever you have in this block. Yes. And the rule, okay, I think I know what the problem is. Okay, just quickly back to the beginning of the lecture on block diagrams. Okay, here. I am actually applying rule 5. Be careful over there when I show the picture. In my case, in this drawing, the signal goes from right to left. Here, the signal goes from left to right. So rule 5 states that if the junction moves upstream against the flow of the signal, then you need to put G1. In this case, the junction moves downstream, following the flow of the signal, and therefore 1 over G1. Okay, so here we have a natural flow, left to right. In our case, you will see when we get back, we have the signal flowing from right to left. So actually it is rule 5. But thanks for pointing that, because that again might confuse. It's not whether you move the junction left to right, but whether you move it upstream or downstream. So here, the signal flows right to left. So I'm moving this junction upstream. And therefore, I'm multiplying. I'm putting G1, not 1 on G1. If you ever get confused, if you are not sure whether this would be C2S or 1 over C2S, think about this. This has to be I2. And this is still EO. So to get from EO to I2, you need to multiply by C2S. It's actually what's written here. So again, this signal must not change. This one obviously hasn't changed. So this has to be C2S. Oh, yes? It is R2, thank you, thank you. It is R2, thanks. So this is R2, thank you. Okay, happy with this. The next step looks easy. Here we have a feedback loop. Okay, what is G1? It's 1. So this becomes 1 over negative feedback loop 1 plus 1 times whatever we have here, R2 C2 S. Yeah, the green is a little bit pale. 1 over 1 plus R2 C2 S. So let's apply this now. Oops, sorry, the other way. Minus. Okay, so our block diagram is getting simpler, simpler. There are still more things to be done. Now again, what you have here looks a little bit like a, deadlock. So again, we are going to move a junction somewhere. And what I'm suggesting is move this junction downstream in this case. So the rule we apply here is not the same as the rule we apply here because we moved upstream against the flow of the signal. Here we move with the flow of the signal. So you'll have to divide by G1. Okay, so let's do it. EI (1 over 1 plus R2 C2S) EO. Now we need to divide by this. So it's 1 plus R2 C2S. And now C1S. Whereas the other one remains as it was, C2S. Oh, sorry. Yeah, I put it here, R1. And the negative sign here. Okay, now I think we are going to make two steps at once. So the first one, which is very simple, is combining these two. They are connected in series. So we are going simply to multiply these two. Do I really have to? Okay, let's do this step only. Okay. So EI summation 1 over 1 plus R2 C2S EO. Here it is C1S into 1 plus R2 C2S. C2S R1 R1 Okay. Now we can hopefully see the light at the end of the tunnel. This part here is what? It is a parallel configuration, because these two blocks have the same input, EO, outputs added together. That is the definition of parallel loop, which means that G1 will be added to G2. Both signs are positive. Okay, so adding these two. Here, negative sign R1 is still here. Okay, we added G1 and G2 together. So that's what we have here. So instead of this red, we have now this block here. Finally, multiply these two, and then apply a negative feedback loop here. Okay. I hope I don't have to show this step. So it's simply R1 times everything here. But the feedback loop, so EI, now G1 is 1 over 1 plus R2 C2S. Down here it is 1 plus what? G1 times G2. So multiplying gives me R1 C1S into 1 plus R2 C2S plus R1 C2S over 1 plus R2 C2S. So R1, C1 over here. Okay, almost there. Let's just simplify this. So EI will be equal to, down here we have C1 R1 C2 R2 S squared plus C1 R1 plus C2 R2 plus C2 R1 times s. Sorry, this was s squared, this s, and plus 1. Okay. Right, so that's actually what we have here, apart from we introduce these constants, T1 and T2. So this is our system, well, our transfer function. Next example is exactly the one we decided not to deal with at this stage from the previous lecture, because once again, this will be an example of a control system. So we'll get back to this particular problem later in this course. Okay. So the last example for today is, not for today, for this lecture, is a situation when you are given a differential equation that describes the system, but you have no idea what kind of system that is. So you can still create a block diagram using the differential equation. Okay. So differential equation only. You have no idea what the system consists of, how those little components are connected with each other. You can still make a simulation. You can still make a block diagram. So if you are given a differential equation like this, okay, how do you create a block diagram where x would be the input and y would be the output? Again, there are a number of ways to do it. What we are recommending here is the best way. What we are doing here is the recommended way, let me put it that way. So you identify the terms that contains the highest derivative of the output, and that would be y triple dot. So express y triple dot in terms of all other terms, x and y and their derivatives. So when you do that, you get this expression here. Y triple dot equals minus 4y double dot plus 5y dot minus 6y plus 3x dot plus 4x. And then you start the same way as before. You put x on the left-hand side as the input. You put y on the right-hand side as the output. This equation here, this equal sign, you represent it with this summation point over here. The result of the summation is y triple dot. All other things have to find their way into the summation. They are inputs into the summation point, into that circle. So you have 4x rather, then you have 3x dot, then you have minus 6y, you have plus 5y dot, and minus 4y double dot. All that should be here. Next thing you do, apply as many integrations as necessary to get from y triple dot to y. That means 3 integrations, but do one at a time. So 1 over s, then 1 over s, then 1 over s. Don't put 1 over s cubed, because you need to separate them to get y double dot and y dot before you get y. Why do you need y double dot? Because you need to multiply it by -4, as you have here, to bring that signal into the summation, -4 double dot. Then you need y dot to be multiplied by 5 and then come back into this summation. That's this second term. Then you take y, multiply by -6, bring it back into summation. So the right-hand side completed. On the left-hand side, you need 4x. You started with x already, so you need to multiply by 4, so you can get 4x coming into this summation. But you still have this thing, 3x dot. So to create 3x dot here, you already have x. You need to differentiate x and multiply that by 3. So therefore 3s here. Okay. So how do you proceed from, so I hope this is clear. Okay, this is the recommended way. As I said, your block diagram may look completely different and still be correct, as long as it describes this differential equation. Okay, I won't solve this block diagram completely. I will just suggest the first step. So the first step is break these summations, that one big summation into a number of summations where you have only two signals to be added or subtracted from each other. Added to each other or subtracted from each other. So if you have x here, and then you have 4, and then you have, what, 3s. Add them together. The next one, just bring -6y here. Next one, bring 5y dot. And the last one, it is -4y. Then you have 1 over s, 1 over s, 1 over s, and then you have y. Sorry, this is -4y double dot here. Okay, apologies. Now, y double dot is here, -4 is here. So connect this. Y is here, 5 is here. Connect this. And finally, y is here. Are you catching up? -6 is here. So next thing, what you have on the left-hand side is a parallel connection. So add G1 and G2 together. Over here, you can do two things. Well, one of the two things. One is to apply a feedback loop rule, first for the inner one, then the middle one, and then the outer one. So 3 feedback loops. So you have one box here, one box here. Just multiply them together, and that will be your transfer function. Or the other way to deal with the right-hand side is to move this point over here. So you have to divide by 1 over s, multiply by s. Move this point across 2 integrators, so divide by 1 over s squared. And then you have 3 additions. And then only 1 feedback loop. So if you don't like feedback loops, go for additions. If you don't mind feedback loops, go 1 feedback loop at a time. You should get the same. You can even practice to see if you are going to get the same thing. Okay, any questions? If not, let's at least launch our next lecture. Now, obviously, you know everything about block diagrams. So, lecture 7, just an introduction. You sound unhappy about something. You thought we would finish 20 minutes earlier. No, we'll finish 10 minutes earlier. Okay, so again, a system with the input and the output. System described by the transfer function, G of S. Transfer function will be, at least in our course, always in the form of numerator over denominator. Numerator is a polynomial of S. Denominator is another polynomial of S. Okay. Now, maybe you noticed, maybe you haven't, using Laplace transform tables, that it is the denominator that determines the character of the system. If you haven't, that's what we are going to show in this lecture. So when you take the denominator, equate it with 0, this is what we call the characteristic equation of the system. So the denominator is otherwise called characteristic polynomial of the system. We're going to see why in a second. If you factorize the denominator, and if you are lucky that all roots of the denominator are real numbers, then you can rewrite the transfer function as a sum of smaller transfer functions with the first order denominators. Okay. And then you can analyze each of these terms separately, as if you have some subsystems in your big system. And you see that when you have a first order denominator, the output will have this exponential function, where the constant in the argument will be actually equal to the root of the denominator, minus d1. And the same here, and so on and so forth. Now, if we can't get all our factors in the denominator to be of the first order, then we'll get them to be of the second order. So when you are factorizing any polynomial, you end up with first or second order polynomials. If you end up with a third order, that means that can be factorized further. A third order polynomial will either have 3 real roots, or 1 real and 2 complex conjugates. That means you can perform at least 1 more factorization there. So no matter how complex your system is, or no matter how complex, how high the order of the denominator is, you can reduce your analysis to only first and second order systems and combine them together. So lecture 7 is about analyzing first and second order systems. We are not going to analyze any higher order systems because they will be a combination, some combination of first and second order systems. So we are limiting our analysis to first and second order systems. And we are going to apply different inputs, 4 different inputs, to see how first order system behaves when you apply those 4 inputs, how different second order systems behave when you apply these inputs. So the inputs we are going to apply are unit impulse, unit step, unit ramp, and unit cosine function. Okay. And as I said, we are going to analyze first order systems. So the transfer function is k over s plus a. And after that, we are going to analyze second order system with the transfer function in this form, k over s squared plus 2 psi omega n s plus omega n squared. Okay. Now, there is only one possible form of a first order system. It is k over s plus a. So we are going to apply 4 different inputs to this particular transfer function to see what kind of outputs we are going to get and how these parameters, k and a, affect the output, affect the response in 4 different cases. The things become a little bit more complicated with second order systems because you may have a different combination of roots of the second order system. So you may have 2 real and different roots. That's case 1. 2 real and identical roots. Then a pair of complex conjugate roots, pair of imaginary roots. So we'll cover 4 combinations. And then, since we have 4 combinations and 4 different inputs, that means 16 cases. We are not covering all 16. So we'll select a few in this lecture, just for you to get the idea how it works. But obviously, at least in theory, you may have 16. OK. So before we do this analysis, do you agree that we stop now? Who doesn't? Let's show. OK. So any questions, either on the block diagrams or the introduction to this lecture? OK, done.
Give me a headache, sir. What is
Oh, really? Oh, that's nothing. Wait for the next week. So that's what you do. So when you set it to be 0, you are getting the characteristic equation. The definition of characteristic equation is this. No. Forget it. Just take the polynomial, make it equal to 0, and this is called characteristic equation. So if I ask you what is the characteristic equation, you say when the denominator equals to 0. I'm not asking what is g over s going to be. It's going to be infinity. That's ds equal to 0. So take the denominator, make it equal to 0, that's the characteristic equation. When you solve the characteristic equation, you get the roots of the denominator. Roots. And now, When you get the roots, that means you can factorize the denominator. Okay? Okay. Once you factorize the denominator, just think about partial fractions. Then you can break your transfer function into a sum of smaller transfer functions, lower order. Yeah. Oh, I don't know. You will get the test back after you get the marks. So marks will be on the Moodle. We said in the course alpha, we said 2 weeks after the test. I honestly hope that it will be less than 2 weeks. But I can't guarantee I'm not marking. So. Oh, no problem, thank you.
So,
Yeah?
for this one, right? Just now you do time apart, right?
Sure.
Just now when you show the example, you split the summation, then you do time apart, right? Is it possible if I just shift the junction all the way back?
Yeah, I think I said that. You either apply 3 feedback loops, or you shift these 2 junctions. You shift by 1 box, this one you shift by 2 boxes, and then solve as a parallel, so you have only 1 feedback loop. And you know what you can do, practice, try it once, try the other, and you should get the same answer.
Okay.
But it is exactly the same. You should get the same.